Welcome to the Explainer. You know, we hear all the time about the massive processors that are powering AI. But today, we're going to look at the hidden magic, the specialized hardware that actually lets those processors talk to each other at truly unbelievable speeds.
Okay, so let's just dive right into this. I mean, what does that even look like? It's not two people talking. Imagine tens of thousands of them, all talking at once, sharing these tiny, tiny fragments of information that absolutely must arrive perfectly and instantly. So it's not just about raw computing power, it's about creating this communication fabric that can handle a level of dialogue we've never seen before.
You know, training these massive AI models, the ones that power everything from our chatbots to huge scientific discoveries, it creates a networking problem on a scale we have just never, ever dealt with. It pushes the absolute limits of speed, efficiency, and reliability, all at the same time. So here's the thing. The really crucial point isn't just one of these attributes, like high bandwidth. The unique challenge for AI is that you have to master all of them at once. You need massive throughput for countless tiny messages, combined with the near-zero delay of ultra-low latency. That demanding combination, that is what sets AI networking completely apart.
It's a totally fair question, right? Ethernet is everywhere. Why not just use that? Well, for a very, very long time, standard Ethernet had a bit of a reputation, a set of perceived flaws that made it seem fundamentally unsuitable for these elite high-performance computing tasks. These four things, they were seen as total deal breakers. The idea that Ethernet was lossy, and I mean that it could just drop data, that was an absolute non-starter. High latency meant unacceptable delays, and its inefficiency with all those small data packets just didn't fit the profile of AI workloads at all. For years, this meant you had to use specialized proprietary networks. It was the only option.
But what if you could take Ethernet and just, re-engineer it from the ground up? What if you could build it specifically to conquer those exact problems? Well, that is precisely the idea behind the Broadcom Tomahawk Ultra, a switch designed to turn Ethernet into the perfect language for AI.
All right, first things first. Let's tackle the biggest myth of them all, this idea that Ethernet is inherently unreliable and just loses data packets.
Yeah, this was the absolute #1 barrier. Think about it. An AI training job can run for weeks across thousands of processors. If you lose even a single packet of data in that whole process, you could corrupt the entire thing, wasting millions of dollars and weeks of time. It has to be perfect, or as they say in the business, lossless.
So, the first tool in the toolbox is something called Link Layer Retry, or LLR. And honestly, the easiest way to think about it is like sending a text message and getting that instant got it reply. Every data packet gets a number and is tracked. The receiver sends back an ACK for a good packet or a NAC if something's wrong, which triggers an instant resend. With a system like this, no message ever gets lost, period.
Okay, so that handles lost messages, but how do you prevent traffic jams from even happening in the first place? Well, for that, you use something called credit-based flow control. This is great. It works kind of like a bouncer at a super exclusive club. The receiver tells the sender exactly how much room it has by sending out credits. The sender is only allowed to send a packet if it has a credit. If the receiver gets busy, it just stops handing out credits, and the flow pauses automatically. This prevents any data from being dropped because of congestion. It's really smart.
All right, let's move on to the next challenge, because you can see how this all builds on itself. We've got a perfectly reliable network now, so the next question is, how do we make it hyper-efficient for the specific kinds of short, fast messages that AI models use all the time?
Yeah, this was the next huge wall they had to climb over. AI conversations, they're not long, flowing dialogues. They're made up of billions and billions of these tiny data packets. And the traditional internet headers, the address labels on those packets, they were just too big and clunky. They created a massive amount of waste.
And the solution here is really clever. It's called the AI Fabric Header, or AFH. I want you to think of it like this. It's like swapping a bulky, multi-page shipping document for a tiny, super-optimized shipping label. This minimal header is laid right on top of the Ethernet frame, slimming down the address to the bare essentials. This just drastically cuts down on waste and makes those tiny packet transfers incredibly efficient. And believe it or not, it gets even smarter. The Tomahawk Ultra uses this thing called in-network collectives. This is a brilliant trick where the network itself actually becomes an active part of the computation.
Common group tasks, like adding up results from all the different processors, get offloaded from the very expensive AI processors and happen right inside the network switches. This isn't just clever. This directly translates into shaving days or maybe even weeks off the training time for a huge model.
So, okay, after all that, after completely re-engineering Ethernet to be lossless, super efficient, and crazy smart, what's the actual payoff? What does this power really unlock in the real world?
First up, latency. The time it takes for a single packet to zip through the switch is less than 250 nanoseconds. I mean, that is practically instantaneous communication between processors. Any delay is virtually eliminated. And to really wrap your head around the sheer scale we're talking about here, get this. The chip can process 77 billion packets of data every single second. That's the just immense throughput you need to keep thousands of hungry AI accelerators fed with a constant stream of information. And that kind of incredible performance is what puts the Tomahawk Ultra right in the sweet spot of what's called the AI scale-up category. This is the engine, the hardware you need to build those massive, tightly connected supercomputers that train a single gigantic AI model, the very models that are changing our world.
So at the end of the day, what's the big takeaway here? It's that progress in artificial intelligence, it isn't just about clever new algorithms or building bigger models. It's also about this kind of invisible, absolutely revolutionary hardware. By solving these fundamental communication problems, technologies like the Tomahawk Ultra are constantly redefining the limits of speed. And in doing that, they're redefining what's possible for AI itself.